Everybody, it's Miss Landry, and today we're going to jump into our second to last lesson about naming. We're going to be looking at covalent bonds. So we've already done ionic bonds, and now we're going to learn about covalent. So let's kind of really quickly review ionic bonds, okay? Let me get a pen here so I can write on the screen. Remember that they're always pretty much between metals and nonmetals. It's supposed to be an arrow. Okay, so the left side of the periodic table and the right side of the periodic table, which means that these bonds are always between cations, which if you remember are positive, and anions, which are negative. Okay, so that attraction between positive and negative is what bonds them together. And with ionic, remember, an electron is being given away by one atom and being picked up by another. So here we have lithium fluoride. It has one single little electron out here. It wants its outer shell, its valence shell, to be full. So this inner one here holds 2. So if it gets rid of that one, it'll have a full outer shell with just 2. And here we have fluorine, right? And it has 7 valence electrons. It wants 8 in this outer shell, so it needs 1. So luckily, lithium will pass it right along, and we get lithium fluoride. Here's another example just to review. Here we have potassium. It has a single valence electrons. Remember, these are Bohr diagrams over here. This is the Lewis dot diagram here, which I find to be a little bit easier. So we have just this single valence electron on the outside of potassium, on the outside shell. So each one of these potassium wants to get rid of it. Sulfur has 2 lone electrons. And so it wants 2 more electrons in order to bond together. So K becomes positive when it gives up an electron, which you can see here. Sulfur becomes a 2 negative when it gains those 2 electrons. And so to balance out together, we get K2S. So that's just kind of a review of ionic. Hopefully you guys remember all of that. So now let's jump into covalent. So covalent bonds are a little bit different. These actually, let's look at what the word means. Co means to share. Valent, you can think of it as valence. So they're going to share their outermost electrons in order for all of them to have a full shell. So if we look at water here, okay, here's hydrogen. It has a single electron in its outermost shell, right? Oxygen wants 2 electrons because it needs 2 more to have a full outer shell. It has 6, it wants 8. Rather than hydrogen giving away its electrons, what it's going to do, if you look right here, is it's going to share those electrons. So if you were to count around this oxygen, there are 8 valence electrons. Hydrogen wants 2, and look at that, there's 2 right there. So they're sharing them. Here's another example right here. If you look at the electrons for phosphorus, they're kind of dark like these right here. So phosphorus has 5 valence electrons. So you know based on the periodic table and based on valence electrons, it needs 3. Okay? But if it binds with something that is not a metal, right? It's going to want to share those electrons. So this chlorine right here is going to share an electron with this one. This chlorine will share here. And then this little electron here is going to share with this one. So now everybody's happy. We're sharing all our electrons, and it looks like this. If you were to draw this, it would look, if you want to draw the bonds, we draw it with a single line if it's a single pair of electrons that are being shared. So it would look like this. Okay, so then over here, just another quick one to show you. You've got carbon with 4 chlorines. This is CCl4. That's hard to write. Okay, chlorine, much like what we showed here, has 1 valence electron, so it needs 1 more valence electron. Carbon has 4 valence electrons. 1, 2, 3, 4. If I do the Lewis dot structure, pretend those are dots, not lines. So that works out perfectly. If I put a chlorine here, it's going to share there. If I put a chlorine here, it's going to share there. Here it's going to share, and here it's going to share. So you just have to think about how many electrons it needs in order to fill the shells for both of them. This is pretty much always between nonmetal and nonmetal. There are a few cases where that's not the case, but for this class, it will be between nonmetal and nonmetal. So let's try, I don't know if I have, yes, I do. Let's try a couple questions. First question, I want you to go through and write down what these are. Are they ionic or are they covalent? Remember that the first thing you ask is there a metal? If there is a metal, it's ionic. If there is not a metal and there's only nonmetals, covalent. Okay, so pause the video, try that out. Okay, so this one is definitely covalent. Carbon is a nonmetal, hydrogen is a nonmetal. Iron, definitely a metal, right? So right there, I know that this is going to be ionic. Let's look at this one. I have K and then NO3, nitrate. I know that K, potassium, is a metal. Therefore, this is ionic. Here I have two iodines bound together. Iodine is a nonmetal, so I have a nonmetal and a nonmetal, so this is covalent. Here I have 4 carbons bound together. Carbon is a nonmetal, so therefore this is covalent. H2O, is there a metal? No, there is not. I hope you don't have metal in your water. So therefore this is also covalent. And then finally, this one here, beryllium is a metal, so therefore this is ionic. Hopefully that was pretty easy for you. Let's try one more. In this reaction that you see down below, which ones of these are ionic or covalent? So I start with this one. I know sodium is a metal. That's always the first question. Is there a metal? So I know that this is ionic. Calcium is also a metal. I know that this is ionic. Look, we have calcium and sodium again. Ionic, ionic. So everything in that reaction is ionic. So that's it for this video. Thanks, guys. Have a good day.